Welcome back, everyone. This is Professor Herring. In this video, we're going to finish up learning from Chapter 16. Specifically, we're going to talk about standard state conditions, the standard states of the elements, and how those relate to the standard enthalpy of formation. We're going to then calculate using the standard heat or enthalpy of formation, and also bond dissociation energies. So let's begin. Before, we talked about how enthalpies of reaction are expressed in thermochemical equations, and that all thermochemical equations are expressed by the enthalpy of reaction. Well, enthalpy of formation is a subset. It's a specific type of a reaction. And specifically, it's where we take elements and they combine to form 1 mole of compound. And this allows us to use the elements in their most stable form as the reference energy. We measure standard enthalpies of formation at a standard state, meaning 1 atmosphere and 25 degrees Celsius. If you were to change the pressure or the temperature, then it would no longer be standard state and the values would change. The symbol here, which is called naught, denotes that the value is at standard state. So we would read this as delta H naught F, or the change in the standard enthalpy of formation. Please note that the temperature here is not at STP, but rather this is at SATP, which stands for standard ambient temperature and pressure. So an example, if we take carbon, its most stable form is graphite, which is solid. Oxygen's most stable form at SATP is gas, and they form 1 mole of compound, carbon dioxide. And the state here does not matter. Because we're talking about a molecule at that point. The enthalpy to make that happen, it would be a negative 393.5 kilojoules. And since these meet the criteria, where we're taking elements, we're combining, we're forming 1 mole of compound, and that we're at standard state, then that means that that's also equal to the enthalpy of formation. So, to summarize, the enthalpy of reaction is equal to the enthalpy of formation when there's 1 mole of a single compound that's created, and when elements are in their most stable state, and of course, this has to be at standard ambient temperature and pressure. So what does that mean then if we form an element? Well, elements have a standard enthalpy of formation of 0. Think of it this way. If you take elemental graphite and you form elemental graphite from it, there's no change that has occurred. Therefore, there's no enthalpy that's exchanged. So the enthalpies of formation for elements in their standard states is 0. If, however, we were to go from graphite to liquid carbon, that would require an enthalpy. That would be non-zero. So, how do we know what the standard states are? These are their most stable physical states when we're talking about standard ambient temperature and pressure. This comes from the ebook. The periodic table that's on the ebook has an option to look at the states of matter. Notice I've checked the standard state box, and therefore these are the states of matter at standard state. What we see is that there are only 2 liquids, mercury and bromine are liquid at standard state. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 gases. And 6 of them are the noble gases, and 5 of them are the others: hydrogen, nitrogen, oxygen, fluorine, and chlorine. And then everything else is solid. Okay? So you only really need to know what are the exceptions. The 2 liquids, the handful of gases, and then everything else is solid. Something to note is that ions are not standard state. So for example, if we had calcium 2 plus with 2 chloride ions goes to form calcium chloride, these are not in their standard state, and therefore the enthalpy of the reaction here would not be equal to the standard enthalpy of formation. Okay? All right. Why don't you try and see if this makes sense to you? Pause the video and try this problem on your own. Welcome back. So we want to know for which one of the following reactions does the enthalpy of reaction equal the enthalpy of formation? So let's just go down. Let's remind ourselves that we need to form 1 mole of single compound and that the elements must be in their standard states. So A is wrong because it produces 2 moles of product. Okay? So this would be equal to 2 times the enthalpy, the standard enthalpy of formation. B is wrong because it's the reverse. It is the negative standard enthalpy of formation. C is correct. The enthalpy of the reaction is equal to the standard enthalpy of formation. D is wrong because it produces 2 moles of product, and so this would be equal to 2 times the standard enthalpy of formation. And then E is not correct because oxygen's standard state is O2 gas, not O3. This is ozone. And we can use the standard heats of formation to calculate the standard enthalpy of reaction for any given reaction. So when they're in their standard states, we can solve for the standard heat of or enthalpy of reaction by taking the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants, where N and M are the stoichiometric coefficients for them respectively. This is an application of Hess's law. So here's an example here. If we want to know how much energy is produced in the thermite reaction, we're given the reaction, and we're given the enthalpies of formation of iron oxide and aluminum oxide. Initially, you might wonder why we're not given the enthalpies of formation for aluminum and iron. But remember that when their elements are in their standard states, the enthalpy of formation is 0. And both aluminum and iron are metals, therefore their standard state is solid. So to find the enthalpy of formation, we're going to take the sum of the products minus the sum of the enthalpies of the reactants, which is 1 mole of aluminum oxide times its enthalpy of formation plus 2 moles of iron minus 2 moles of aluminum, which is 0, and then also subtracting the 1 mole of iron oxide. Combine that to get negative 851.5 kilojoules. If you want to see the thermite reaction in action, go look at figure 16-4-3 in the ebook. It's really cool. All right, go ahead, pause the video now, and try this problem on your own. Welcome back. So, again, for combustion reactions, it's expected that you should be able to draw out a chemical reaction on your own. So you should have been able to get this. You're given the enthalpies of formation for sucrose, water, and carbon dioxide. We know that for oxygen, because it's elemental, it's going to be 0. So to find the enthalpy of reaction, we can take the sum of the enthalpies of reaction, or excuse me, of formation of the products minus that of the reactants. So this will be 12 enthalpies for 12 carbon dioxide plus the formation of 12 waters minus the enthalpy of formation of 1 sucrose plus 12 oxygen molecules. So we have 12 carbon dioxide plus 11 water minus the 1 mole of sucrose and the 12 moles of oxygen. Again, because this is in its standard state and it's elemental, it's going to have a standard enthalpy of formation of 0. Do all the algebra, and you get negative 5,644.1 kilojoules. The last thing to talk about in this chapter is the bond dissociation energy. This is the energy that's required to break a bond in the gas phase. And we already talked about this a little bit when discussing covalent bonds. We said that bond dissociation energy is the energy required to break covalent bonds, and that was it at that time. But now we're going to realize that it's equal to breaking the molecule essentially in half or into pieces in the gas phase. So for a diatomic, we can do this with just a single chemical reaction, where we take the hydrogen, we break it apart, and they actually become hydrogen radicals. The bond dissociation energy there is 436 kilojoules per mole. For polyatomic elements, the bond dissociation energy is obtained by averaging over many different molecules. So for example, for water, we would see that to break the oxygen-hydrogen bond, it's 494 kilojoules per mole. But if we just look at hydroxide, it actually is less energy. And so when we look at the OH bond, it's actually an average of that. So what we see then is that bond dissociation values are not 100% accurate for any one case, but they're a good enough approximation that we're able to use them. We're able to use bond dissociation energies to estimate the enthalpy of reaction for any reaction. This is another application of Hess's law. And so to review what we've talked about before, when we break bonds, that's going to be endothermic. When we form bonds, it's going to be exothermic. And so if we look at the overall reaction of ethane reacting with chlorine to make chloromethane, what we can do is we can break the bonds between the carbon-carbon bonds. We can then break the chlorine-chlorine bonds, and then we can combine the chlorines with the carbons to make a carbon-chlorine bond. And so this is just applying what we've already seen in general about Hess's law, is that the sum of these steps is going to be equal to the net reaction. And so we use this expression, which is taking the sum of all of the steps. So this is on your data sheet as well. And that's the sum of the bond dissociation energies for the bonds broken minus the sum of the bonds formed. Now, we might ask, why is it bonds broken minus bonds formed? Because typically, we talk about products minus reactants. And for bond dissociation energy, it appears to be the reverse. Because again, if we look at, let's just say we have A and A reacts with B and B, and that gives us 2 AB molecules. We're going to take the sum of the bonds broken minus the bonds formed. But we break in the reactants and we form in the products. So why is it the reverse? Well, as I said before, bonds broken requires energy. So that's going to be positive. Whereas formed bonds give off energy. And since really what we're doing is taking a sum of all of the steps, really the enthalpy of the reaction is the sum of all bonds, broken or formed. But some of those bonds, the formed bonds, happen to give off energy and therefore are negative. So it's really the sum of all bonds broken and formed, and some of those bonds will be negative. Let's do a practice problem. So in this case, we're looking at the decomposition of hydrogen peroxide. You're given the bond dissociation energies, and we want to find what's the enthalpy of the reaction. First thing to do is make sure that your equation is balanced. We have 4 hydrogens on the left and 4 on the right, 4 oxygens on the left, and 2 4 on the right. The next step is to draw the Lewis structures. The reason why you have to do this is because we're looking to break the specific bonds, and we need to know what those bonds are. So we have 2 hydrogen peroxides, and they react to form 2 waters and 1 oxygen. The next step is to count up the bonds broken and formed. So for each bond type, we see that we're going to break 2 oxygen-oxygen single bonds and none on the right. We don't form any. So we have a net of 2 broken. Oxygen-oxygen double bonds, we have none that are broken, but 1 that's formed. Oxygen-hydrogen, we break 4 on the left, we break and we form 4 on the right, so there's no change. For hydrogen-hydrogen, none are broken and none are formed. So that means our net is going to be 2 broken oxygen bonds and 1 formed oxygen double bond. So now we find the enthalpy of the reaction by using the net bonds broken minus net bonds formed. The broken bonds is going to be 2 oxygen-oxygen single bonds, and the formed bonds are going to be 1 oxygen-oxygen double bond. When we plug in our values, we get a total enthalpy of reaction of negative 203 kilojoules. This is the enthalpy of the reaction, meaning it's written as is. So that's for 2 hydrogen peroxide. We want to know what's the enthalpy for decomposition of 1 mole. So to find that, we need to take our enthalpy of reaction and divide by the ratio, which is 2 moles of hydrogen peroxide, to get negative 102 kilojoules per mole. When you do the reaction itself, it turns out that it's actually negative 94.6 kilojoules per mole. So it's pretty close. Remember how we talked about that for different molecules with those types of bonds, we average over them. And so it's going to introduce a small error. Okay, for the last one, I'd like you to try this on your own. Pause the video and try this before watching through the solution. Welcome back. So the first step is to make sure you have a balanced chemical equation. This is a combustion, so you should be able to get the following reaction. The second step is to draw the Lewis structures. We have 2 propenes, and 9 oxygens. We have 6 water and 6 carbon dioxide. Then we look at we sum up the bonds broken and bonds formed. We have our different bond types represented, and then we can go through. We have 2 carbon-carbon single bonds in our reactants and none in the products. So we break 2. Carbon-carbon double bonds, we have 2 in the reactants. Again, this is because we have 2 of the propane molecules. and we have none in the products. Carbon-oxygen double bonds, we have none in the reactants, and 12 in the products because there's 2 per carbon dioxide and there's 6 carbon dioxides, a net of 12 formed. Carbon-oxygen single bonds, we have 9 that are broken and none that are formed. Oxygen-hydrogen single bonds, there's none that are broken and 12 that are formed, 2 per water molecule and 6 water molecules. And then carbon-hydrogen bonds, single bonds, there are 12 that are broken, 6 within each propane, and none that are formed, for a net of 12 broken. The enthalpy of reaction is bonds broken minus enthalpies of bonds broken minus those of bond formed. And so that's 2 carbon-carbon single bonds, 2 carbon-carbon double bonds, 9 oxygen-oxygen double bonds, 12 carbon-hydrogen single bonds. Those are all the bonds that are broken, and we subtract the enthalpies of those that are formed, which is 12 carbon-oxygen double bonds and 12 oxygen-hydrogen single bonds. When we plug in our values, make sure that you're reading them properly from the table. 2 carbon-carbon single bonds times its value, 2 carbon-carbon double bonds times its value, 9 oxygen-oxygen double bonds times its value, etc., etc. You add all of that up, and you get a total of negative 3,809 kilojoules. If you say that was your answer, you're not quite right, because remember, the reaction is listed for 2 propane, 9 oxygen, 6 carbon dioxide, 6 water, but we want to know for 1 mole of propane. So we need to take and divide by 2 moles to get negative 1,905 kilojoules per mole. That's it for this video. Thanks for watching. If you have questions, you can ask on Piazza, in office hours, or recitation. See you later.